Okay, what we want to do today is not to try to teach you anything about how to do biostatistics. That takes a little bit more than an hour, but to give you an idea of why you want to mess with it, what it'll do for you. We're going to look first at a fairly simple example, because it makes a lot more sense to look at these characteristics through the prism of an example that's meaningful in medicine. And then I'll end up with a few examples of how statistics might be misused. Some of them are kind of interesting. Overview: what statistics can offer. Well, what is statistics? It's trying to choose what acts we'll do, what we will do under conditions of uncertainty. We can't get rid of uncertainty, it's always there, but what we can do is we can measure that uncertainty, and we can select our action under the conditions imposed by that measure. You want to walk across the street. If a car is bearing down on you, there's 1 in a million chances of it hitting you. You decide to go. That's your act. If it's 1 in 10, you wait. That's your act. That is based on the measure of the uncertainty. Statistics allows you to weed through data, find out what are the important things, what are the irrelevancies. It allows you to get around biases that might otherwise deteriorate your data, impair it. It allows you to get the maximum information out of your sample size, often at this hospital fairly small samples, because a lot of the research done here is for teaching purposes, and they want to have the time period into that which can be accomplished by a resident and finished before the residency is finished. If you have huge amounts of data, it allows you to dig down, get the nuggets of gold out from the gold mine, and it also provides evidence. When you say evidence-based medicine, what is the evidence? It's mostly statistical evidence. It reduces a lot of inadvertent errors. Sometimes you get egg in your face if you don't do statistical planning and statistical analysis. But what won't it do? Yeah, it won't make uncertainty disappear. You can't get rid of that. It won't give you answers without work. You can't take your numbers, dump them in a software package, come out with some answers, and go with it. You have to choose the right methodology for your particular problem. It won't give you good answers from bad information. If you don't take the right data, you're lost. Statistics won't recover for you what you don't have. Now I'd like to start with this little example. I made reference to Russell Mapes and Bill Henricus. Used to be at this hospital, and this little study was done here. It's a case of supracondylar elbow fracture. The question is, do you want to cast it pronation or supination? Which is better for healing? Okay, we say that blood flow is a marker for better healing. So we want to get as much blood flow as we can into the injury site. So after pinning, they start measuring pulse with the Doppler and flex the arm, in the two different positions until the blood flow cuts off. And they measure the angle of flexation. Which method gives the greater angle? Okay, we'll step back a little bit and say, what is the objective of statistics? Well, really what we're trying to do is to make a decision about a population based on a sample from that population. Okay, what is a population? Well, it's all members of a group, and the group to which you wish to generalize, about which you would like to be able to make a decision. And a sample is a subset of that. What can be a sample in one case can be a population in another. If you're trying to make some conclusion about this hospital, then a department is a sample and the whole hospital is the population. But if you're trying to make a decision about military hospitals in general, then this hospital as a whole becomes just a sample instead of the population, and all of the military hospitals become the population. We also have the idea tied in with this uncertainty issue that I raised earlier. To try to control or limit it, we have what we call alpha, is the risk or probability of being wrong if we decide that a difference in treatment or response exists. Now, in terms of this, we can restate our example. Based on a sample, we conclude that a treatment difference exists in the population if the risk of being wrong is smaller than this alpha. We generally, by convention, take alpha to be 5%, 5 fingers. It's not cast in stone. You can do something else, but since 5% is so common, you usually have to justify it if you do something different. In our example study, we could say we will infer a difference in blood flow between pronation and supination casting if the sample estimate of the alpha, and we call this estimate of the alpha taken after you get your data, we call it a p-value, if that's less than 5%. And if you do find a difference, then the larger mean angle, that is, the further the elbow can flex without cutting off blood, is the better method. Well, what could go wrong with this study? For one, representativeness. We can generalize only if the sample represents the population. Has to look like it in lots of respects. And a nice example of this is a resident I had one time who was trying to make a conclusion about the population of American men in general and took a sample from the Marine Corps recruit depot. So he had young men in peak physical condition, and they hardly represented the population. This was a bias. So how can we see that we do have representativeness? One way is to sample from a population randomly. And what do we mean by randomly? What is randomness? Randomness is allocation to the arms or groups of the sample, unknown in advance, designated only by chance. So in other words, flip of a coin, roll of a die, spinner, random table, lookup, computer random generation. Those are ways to get things to occur, get numbers by chance alone. It does not mean taking one patient in one arm, the next patient to come in the opposite arm, and on like that. Does random mean equal likely? Well, not really. If you, for example, took a die, painted one face red and rolled it, you'd have 1/6 probability of getting red. That's still random. Only chance is deciding it. But you get 5/6 versus 1/6. It's not equal likely. Bias is what we call a deviation from representativeness. There are any number of types of bias. We can't deal with all of them, but we can look at some of the more common ones, and probably the handful of most common ones are these. Lack of demographic balance. Well, I gave an example of the Marine Corps recruit depot, which was not demographically the same as the population of American males. Method of selection. You may have a time of day or day of the week. If you have one group of patients coming in more at one time than another, then you would have a selection bias if you pick a particular time to do your sampling. Missing data, one of the best examples is the Connecticut Cancer Registry, the first cancer registry in the country, which was started in 1941. They took data from their files back to 1936. After a while, they kept finding discrepancies. They were very unhappy about it. They sought the source of this discrepancy, and they found that a lot of the patients had died and were no longer in the database. Other patients had, well, if not gotten well, at least had no evidence of recurrence and were lost to the database. So the only patients they had from 36 to 41 were just patients who had continuing bouts of cancer, and this was a case of missing data. Comorbidities. Maybe you're doing a liver study and some of your patients have hepatitis, some don't. That can influence it. Reporting. Lots of patients do not like to admit to STDs, and that's a reporting bias. So we have any number of types of bias. We can design our experiment often to reduce the bias. If we just look at anecdotes, well, you've often heard somebody say, oh, that's only anecdotal, so it doesn't mean anything. Well, it doesn't mean a lot, but it means something. If somebody takes, say, a complementary treatment and gets well, that's a datum. What it doesn't tell us is how many took it and didn't get well. So if we want to look at effectiveness, we need to go to a registry where we find who did it, who didn't, and what the result is. Well, that doesn't really have any control over it. The one way of controlling is a case control. We take patients who have a particular disease, we treat some and not others in a certain way and see what the difference is in recovery. Or looking at cohorts, we can control for the risk factor. We get a group of people, follow them over time and with different treatments and see who develops difficulties and who doesn't. Often you're constrained to do these things. You don't have a choice, but if you have a choice, a better procedure would be to do prospective planning. You set out, get a group of patients, randomly allocate them into groups, and then use different treatments for the different groups and determine what the difference in outcome is. If you randomize this, you have an RCT, a randomized controlled trial. And finally, if you mask it or blind it, so the patient and experimenter do not know who's in which arm, then they cannot influence it. And this influence is not necessarily chicanery. It may be inadvertent, unrecognized even by the investigator if he wants to see a certain outcome occur. Steps in setting up a test. You want to find out, is there a difference between two arms? The question asked of our data. Okay, in our example, the question is, which way do we cast the arm for best elbow healing? A variable to answer the question, the amount of blood flow that gets through to the injured location. The descriptor of the variable, the amount of flexion required to stop the blood flow. Null hypothesis, there's no difference between pronation and supination. Alternate hypothesis, one is better than the other. Then we select our risk of error, say 5%, as is common. We choose a hypothesis test. Which test do we choose for that? We'll have to look at that in a minute because it's a little more involved. So we'll come back to that. We describe the population. The population of American children. Our sample, a group of children from who are dependents at this hospital. Verify that the sample size is adequate. Oh no, that's a sticker. So let's look at what we call a power analysis. Look at just the left side for a moment. Here we have zero difference down here. These are differences between the two and standard errors. So we call it the null distribution. This is the data vary about this zero value. That's if the null hypothesis is true. If the alternate hypothesis is true, and we don't know how much it is, but I've drawn it as having 3 standard errors distance here. This is a clinical difference we need to put in. We decide how much difference do we want to try to detect. What is important clinically? How much of a difference will make you change your treatment of the patient versus how much do you not care? You get a simple example of temperature. Patient is 37 degrees Celsius. You get a ½ degree. Do you worry about that? Not really. You don't pay much attention. You get 2 degrees. Oh yeah, big difference. Where in there is the cut point where you feel I'll treat this patient differently if the difference is more than a certain amount? So you make that decision. We choose alpha. We choose a beta. Alpha is the risk of a false positive. That is, there's no difference, but it just by chance falls on the right side of the decision point here. So the area under the curve, that is the frequency of occurrence in the distribution in the decided difference, even though it came from the no difference, is alpha. The risk of a false negative, if there really is a difference, but just by bad luck, we happen to fall in the decision area of no difference. That's the other type of error. So you say how much alpha and beta you're willing to risk. By convention, beta is like 10%, 20%. Power is 1 minus beta. So if you have a power of 80, that means a beta of 20%. And finally, the last thing is a standard deviation of the data. Now, if you can see down here, it may be out of sight, I hope not. We have the standard deviation of the data over the square root of the sample size. Now there's where the sample size sneaks into this thing. That gives you the standard error of the mean, which is what we have plotted over here. Now to go from this configuration to this one over here, we have the same distance between them, we have the same means, we have the same decision cut point. What I did is to take the sample size 4 times over, and by the square root that means we get half of the standard error. So now you see how the curves skinny down and you see what happens to alpha and beta. So the concept of a power analysis is we choose alpha, beta, our clinical difference, and we get an estimate from somebody else's data of what standard deviation is. We plug those things in, and then we let n increase until we reach our target alpha and beta. And that gives us an idea of how much. Okay, how accurate is this? Well, I've had people say, it says we need 73 people, so I can't get by with 72 and I don't need 74. Not at all. We're taking somebody else's data for our standard deviation. It's not our data. It's certainly going to be different in some way. We're choosing alpha and beta out of the air. We're putting in the clinical difference as a judgment on our part. So we put 4 squoozy values in. What did I say about making a silk purse out of a sow's ear? If you put in squoozy data, you're not going to get a good solid datum out of it. So if it says you need 73, what this means is you probably need more than 50, you probably don't need 100. It's very much of a ballpark thing, this power analysis business. Well, in our particular example, we chose a clinical difference of 3 degrees. We thought that's the amount that would be clinically indifferent. Less than 3 degrees, we won't notice a difference. It's just variability. Alpha's 5%. We chose beta as 10%. That is a power of 90%. Our estimated standard deviation was 4 degrees, and so we came out with n is 19 is what we need to get this kind of a result. Right. At this point, you can take your data. What? You already have all your data? Bad. You might not have the right sample size. You might not use the right variable. You might not have a sample which is properly controlled. Any number of things. You want to plan first. Now, that's not an imposition on you because you're going to do all this stuff sooner or later. So you may as well do it up front and make sure you get it right. I, being super lazy, like to do the least amount of work, and the least amount of work is to organize it first and not try to backtrack and clean up things that weren't done right. Okay, so you do your planning, then you take your data. After you get your data, you can test and see if you have any errors that slip by, and you can carry out your final test and form your conclusion. Here are the data. Pronation degrees, supination degrees, and we also notice that we have age and sex. Well, might they bias it? Speaking of sex, we know that in adults, men tend to have more muscle mass, women more fat mass. Might that be lodged in an elbow? Does that happen with children? We don't know, but it's possible. So we'd better just check it out and see if we have a bias due to sex. And age? Well, toddlers have a lot of baby fat. As kids grow older, they skinny out and they get stringy. Maybe age has some influence on the compaction in the elbow. So we better check both of those things. Here is a distribution by male and female. We did a test on this, and we got a p-value of about 0.68, which is not significant. So we conclude that there's no bias due to sex in our data. Age. Well, age is continuous, so we had to do a scatter plot here, and we get a correlation coefficient between age and the difference in degrees between the two forms of casting. And we find that our correlation coefficient is about 0.26. It's pretty low. It's not very impressive, and if we test it, we find it has a p-value of about 0.25, way bigger than 0.05. So again, we have no evidence that age has influenced our sampling. Okay, now here are the data. What we'd like to do maybe is do a paired t-test. You've all heard of those because you see it so often in the medical literature. But a t-test assumes we have a nice bell-shaped distribution. That's not very bellish. So we have to go to rank methods. Okay, to decide on what test we want to use, this is going back to earlier I said we'd meet this later. What type of data we're dealing with? Is it continuous or categorical or ranked or what? What's the question we're asking? You can ask a lot of different questions. You need to make the question very precise. Then what kind of population distribution are we dealing with? What can we assume? How big a sample do we have? How many arms do we have? How big an error are you willing to put up with? Here's a part of a little table. Type of data, categorical, ranks, continuous, questions about proportions or counts or averages. The distributions you assume. Over here, small, large samples, how many groups. What we've got is one group because we have paired data. We have continuous data. That's the angle you've measured. We want to know, is the average of the difference between them other than 0? But we cannot assume normality, so we go to non-normal. Rank methods. We got to go over here and start over. Okay, one group, small sample, signed rank. There we are. That's what we're going to use. What we do with signed rank is we take all of the data. You saw that nice long list. Assumedly, some of them are positive, some negative. When pronation is bigger than supination, it's negative. When supination is bigger, it's positive. So we take these, this list of data and we rank them without the signs. Then we stick our signs back and separate them, pull them apart to where we have the positive signed ones and the negative signed ones, and we add up our ranks. Then we calculate the result. We look it up in a table, and we found in this particular case a p-value of 0.002. It's only 2 times in 1,000. Would we be wrong if we said there's a difference between these two casting forms? Highly significant. So the treatments are different. We look at the means to see which is which. Pronation cuts off at 111 degrees, supination at 115 degrees. So we conclude that supination is better. All right. How did statistics help us? It clarified just exactly what question we're asking. It wasn't a vague question like, which is better? Which very often, that's a good starting point, and residents will come in with that kind of a question. We need to specify it down to where we can quantify it. We identified the variable that answered the question, blood flow. We identified a measure of that, the cutoff angle inflection. We verified that we had a big enough sample. We took 20 when our power analysis said we needed 19. We tested for bias, no sex bias, no age bias. And we answered the question asked. Supination gave us a better result. And we limited the risk of error. 2 in 1,000 is our risk of being wrong in this conclusion. And there you have our example. I went over that fairly fast. You have the handouts. You can go over it again. Let's look at a few examples of misusing statistics. It can be done by accident or because the user doesn't know what he's doing, or he can actually spin or lie. And we have all been watching politics enough to know that that happens. Here's an inadvertent use, just not very good thinking. People confuse absence of evidence with evidence of absence. Any number of times I've seen something come up, perhaps a complementary form of medicine. They'll say, it's no good because there's no evidence, no study's been done to show it's good. Well, that's absence of evidence of effectiveness. That's not evidence that there is no effectiveness. The example here, in JAMA, 35,000 men showed no evidence of a drop in prostate cancer from taking vitamin E. So we have a big headline, vitamin E is useless in preventing cancer of the prostate. We could talk about this in a lot of ways, such as dosage, frequency of dosage, things like that. They use one dosage and one frequency, but the big issue is other possible causes. They pooled people of all different sorts. If you separate them out into subgroups, a study of smoking men in Finland, and this was a huge sample, showed a third reduction in prostate cancer rate from vitamin E. So keep those two things clearly separate. Fashionable thinking. It's gotten very fashionable nowadays to say that nothing is useful without having a randomized controlled trial. You can't believe anything else. Well, there are cases where we do. I submit that if you jumped out of an airplane, it would be advantageous to your health if you had a parachute. And the British Medical Journal in 2003 did a coverage of that, showing preventing major trauma as a result of gravitational challenge. No one has done a study to find out if parachutes are effective. And so if you go with this fashionable thinking that you can't believe it unless you've got a randomized controlled trial, well, go ahead and jump out without the parachute. Misuse because you don't understand statistics enough. How about correlation? Measure of head trauma and brain injury had only 0.013. I mean, had a whole 0.013 p-value. Said that wrong. Had a small p-value, which makes it very highly significant. But the correlation coefficient was only 0.07. It's very small. The point is, if you know enough about statistics, you know that you'll always get a significant correlation coefficient if you have a big enough sample size. If you don't get it, increase your sample, increase it, and then you've got your significance. It doesn't mean that it has any meaning. If we say gullibility is accepting a result that's not supported by evidence, we could say reverse gullibility is failure to accept a result that is supported by evidence. The really historical case of this was Semmelweis in Vienna in a maternity hospital. It seemed that 18% of the women who were treated by male physicians died. They got puerperal fever. So Semmelweis tried washing hands between patients, and he cut the death rate down to 1.2. That's pretty convincing. If we did a test on it, they didn't have the statistical tests in those days, we would find a very, very small p-value. It would go 0.0000 all the way out to the wall over there. But they wouldn't accept it. They knew what was right, and that was of no value. They just knew it. So they didn't accept the evidence, and they degraded Semmelweis. They took away his hospital practicing privileges, broke his spirit, and he eventually died in a mental hospital. And of course, along the way, thousands of women continued to die unnecessarily. News media. Fatal blood clots from oral contraception pills that had been 1 in 7,000. Now they had a second case. They had one case before. Now they had a second case. So it went up to 2 in 7,000. So the media that makes their money from headlines, getting people to read, reported that as a 100% increase in risk from the new contraceptive device or pill. And that led to 13,000 extra abortions in the United Kingdom, increased teenage pregnancy, and a huge cost to the National Health Service. Well, you get people that are pretty fanatic about certain issues. And you've heard a lot about women being underrepresented in medical trials. Well, I came out with a statistic. NIH clinical trials, only 14% were for women. Oh my word. Doctors are just terrible. They're giving women short shrift. They don't care about women at all, do they? Only 14%. But let's drop the other shoe. 76% of funding is for both men and women. That means 90% of funding include women, so that for men only is only 10%, much less than the 14% for women only. So this is not a very valid claim. Okay, let's look at a fanatical issue. Someone wishes to show that when you put silicone implants in women's breasts, it doesn't increase the silicon level. If they found a correlation between the op and post-op silicon levels, then you could say that silicon level was already there, so therefore it couldn't be due to the implant. So let's show that. So we do a pre versus post-op scatter of data and put a regression line through it. Well, gee, the data are all over the place. That's going to confuse the public. We better not have that. We'll just take them out. Well, the regression line is still pretty horizontal. That's not going to be convincing. Let's blow up this section of the axis, or vertical axis. Now we're getting somewhere. We can show a good relationship, but gee, if people read these things, they're going to see the difference between the two axes, so we better just cut off those. Now we got it. Post-op, pre-op, big line going up, proof. So you sort of sneer and you think, oh yeah, you think that doesn't really happen? Well, I found this just last month. This axis, less. And there's our curve. Nice, smooth curve that has a cubic shape to it. I can't imagine they had any data for that. Anyway, that really happens. A few other quick ones. Users of Crest toothpaste have 23% fewer cavities. That's fine. Fewer than what? They don't say fewer than what. Brushing with sulfuric acid. This is a nice one. Nothing cures headaches better than our drug. Okay, for this one, we've got to have a marketing guy and a technical guy. Technical guy says, I'm very sorry, sir. We did the study and we found that placebo gave us more benefit than the drug. Marketing guy. What? Placebo. What's that? Oh, well, that's really nothing. It's a sugar pill. Not to worry. Headline. Nothing cures better than our drug. Okay, to close out, it's about time. A couple of amusing ones. So they added instead of averaging. Obesity tripled in the past 2 decades. 24 million adults are now overweight or obese. A fifth are men and a quarter are women. What are the rest? Chimpanzees? And finally, this one. Okay, they require that I put on a discussion. So, do you have any questions or comments or anything you'd like to talk about? We have 2 or 3 minutes, I guess. Well, all right. Finally, they require that I put on more information. I listed my favorite book first. That actually was written at this hospital, data from this hospital, using research examples conducted at this hospital. So it's very appropriate to the things we do here. Then these are some other pretty good books. This Armitage, that's really a terrific book.